let us start out at the bottom with the graph, okay? All right. And we're going to see if you guys can tell by looking at this. I'm just going to draw a general shape. Yep, draw that general shape. Nope.
Teacher pay for equal.
Doesn't matter. Draw the general shape. We're not going to get specific. Just the general shape. Five, four, three, two, one. So yesterday we talked about critical points. Critical points. Critical points are points where the derivative is equal to or the derivative does not exist. So you guys tell me when I get to a critical point. Why? It does have an arrow, so I'm not going to call it an endpoint. So that's a critical point because it is a corner, okay? And you cannot take the derivative at a corner. So that's one spot. Tell me another spot. Yep. That's a local max. We know that f prime is equal to 0 at that spot. That's a local min. And again, we know that f prime is equal to 0. And those are the three critical points we have on the graph. So just to bring you back, had a student during first hour. They're very inquisitive. They had the function p of x is equal to x to the fourth minus 16. And what we discovered about that graph was that it looked like this. It went through positive 2 and negative 2, and it went all the way down to 16. Okay, probably should have drawn it like that. We'll try one more time. So the graph looks something like that. It went through negative 16, it went through negative 2 and positive 2, but they're like, well, how far does it drop down in those situations? That's called hidden behavior. We want to try to address that hidden behavior in this class, but in order to first address it, we have to identify that they are critical points and where the derivative is equal to 0. So in this one, you tell me when I get to a critical point. Yeah, we would say vertical tangent. Okay. Yep, that's a local min where f prime is equal to 0. Yep, that's where f prime, again, is equal to 0. That's a local max. Endpoint. And how about here? Not here because this is not really part of the domain, is it, in that situation for the spot? There's no outputs. This is not a point we would say at that spot, we would say. So at the value of 7, 8, 9, at 9, we would say you do have a critical point, and it is right there. We wouldn't say there. Doesn't really matter. I'm not going to try to trick you down on the test. But so that's what we're trying to do algebraically is to determine those. So I'll take the derivative, f prime. How do I take the derivative? Quotient rule. Derivative of the top times the bottom would be t squared plus 1. Minus, what's the derivative of the bottom? 2t times t. And that's all over t squared plus 1, that quantity squared. Now, this is something you're going to use as we move forward in this class. Please pay very close attention so you understand why. F prime of t is then equal to, what are you going to have in the top? Negative t squared, or 1 minus t squared.
Wait. How do you use that?
So this is 2t squared, and then t squared minus 2t squared is negative t squared. So I want you to tell me something about the denominator. It's squared, good. What else?
It's like
Great idea.
I was thinking that too.
True or false? The denominator at some time will equal 0. Absolutely false. Why? Yeah, look at all the things that are making this positive. You square something, it's going to be positive unless it's 0. Add 1, then it's definitely positive. And square it, it's positive again, right? You should be able to look at the denominator and say, that will never be negative. It will never be 0. Okay? Can the top be equal to 0? Yeah. In fact, if you were to factor this to 1 minus t times 1 plus t, okay, and the bottom we have t squared plus 1 quantity squared, notice that your critical points are happening at t is equal to positive 1 and at negative 1. So what that means in our original graph, we probably have a local max or local min or something happening at 1 and negative 1. I'm going to take out my calculator. You don't have to, but I'm going to because it's fun. And I would like to verify that I for sure have that, because I don't know what the graph of t divided by t squared plus 1 looks like. So I'm going to look at this graph, zoom standard. Ooh. And I'm going to look at my window and take my y min to negative 1 and my y max to positive 1. Does it look like I have a local min and local max at negative 1 and positive 1? That's what you found algebraically by that work right now. Okay. All right, let's try the next one. What does a cube root look like? So a cubic looks like this. A cube root looks like that. So as you look at the graph, are you going to have a critical point?
No.
Yes, because you have a vertical tangent, right? So when we take the derivative, we should be able to find the vertical tangent. So let's see if it comes on up. This is g of y. I should say g of x. Sorry about that. Anybody know how I take that derivative? Chain rule. Very good. What goes on the outside? U to the 1/3 and then 3 minus x. What is the derivative of 3 minus x? Negative 1. And the derivative of u to the 1/3? Good. So as I multiply these, I get a negative 1 on top, and on the bottom, I get 3 times the quantity, 3 minus x, raised to the 2/3 power. Is the top ever equal to 0? No. Is the bottom ever equal to 0? For what value? 3. So x equals 3, I have a critical value. Now we made the prediction that as we look at the graph, it should do that vertical tangent piece. So I'm going to quick sketch that graph. I could just press math and grab my cube root function, which is number 4, and type in 3 minus x. And I'm going to zoom standard, and let's see if at 3 it does that vertical tangent piece. And sure enough, it does, doesn't it? And if you don't like the graph, you could go ahead in your window and change the min to a negative 3 and a positive 3. It'll give you a better view of that vertical tangent. We all good with that? Good. Okay, 2 more here. This is the bird function. Anybody remember sketching the function that looks like that last year a little bit? That's what this one makes. So if we have that as a shape, does that have a critical point? Yeah, right here, wherever it changes, right? Because The derivative from the left is the same as the right. You have a corner there, so that should pop up in this situation. So as I write this, I have y is equal to 1/4 times x to the 2/3. So that's something you have to just kind of start to see as we've taken derivatives, how to work with those functions to put it in a form where you can take the derivative. So what do I do here? Y prime is? Drop the 2 in front, I get 2 over 12, or 1 over 6 times x to the negative 1/3. Or in other words, y prime is equal to 1 over 6 times the cubed root of x.
So the numerator is equal to anything, but we're going to get something out of that.
So when x is 0.
When x is 0, we should have a critical point. To show that, I will quick go to my calculator. I have x raised to the 2 divided by 3. I'm going to divide that result by 4, and I will zoom standard. Tough to tell there because it's so flat, but I'll take the window and I will have my y min be a negative 2, my y max be positive 2. Let's see what we get now. What do you think? Critical point at 0? Sure enough.
How did you get here? Like,
So I'm looking where the denominator is equal to 0.
So we'll
how
go
did you
with
get
0,
that fraction?
Yep. See that?
Mr. Dennis, how
Yeah.
did you get that fraction?
Do you see how I have this?
Yeah.
So 1's on the top, 6 is on the bottom. Since x is to the negative 1/3, it goes to the bottom.
Oh. Okay, yes.
So what number would you plug in for x to make 0 in the denominator?
0.
Bree, what number would you plug in for x to make 0 in the denominator? Just 0.
Yeah. Well, yeah, that makes sense.
If it was 1 over 6 cubed roots of x minus 2, then it would be 2 that would make 0 in the denominator. But since it's just x, 0. Better? Okay, last example. I don't know much about the graph of sine of 2x plus cosine of 2x. I really don't. But I do know how to take this derivative. What do you do to take the derivative of sine of 2x and cosine of 2x? The chain rule. Yep. We have sine of u and we have 2x. Cosine of u and 2. So what's the derivative of sine of 2x? 2 cosine of 2x.
Plus negative 2 sine.
Very good. When you do the other one, it will be a minus 2 sine of 2x. Okay. Now this is a little bit different. This involves trig, right? So we'd really like to know where this is equal to 0. So, how am I going to solve that?
Yes, plug in. I guess get x by itself.
So, Patty's got some good thoughts here, but how are you coming up with any of that?
Take the highest or that wouldn't be it, but you like highest over 80.
I'm going to add the 2 sine of 2x over the other side.
Yeah, thank you. Thank you.
Okay. So I'm going to, multiple ways of looking at it. I'm going to subtract or just add the 2 sine of 2x over the other side. Anybody know what I want to do now? I'm going to divide by 2 cosine of 2x. Okay. What do you end up with on the left-hand side? The 2's cancel. And what's sine over cosine? So I get tangent of 2x is equal to
So once again,
1. Okay? So, does anybody remember where tangent is equal to 1? At pi over 4. That's where your So that's where your x, y values are the same. So you can see here that at pi over 4 it's 1 because that terminal point is the root of 2 over 2 and the root of 2 over 2. And if you were to divide those, you would get 1. Remember? Okay, if you don't remember, that's fine. Here's the other way of going about it. I will show you. Okay, so if you don't remember that it's pi over 4, then here's what you could do instead. You could do tangent inverse of 1 on your calculator, and this value is pi over 4. Okay, so you could just write down the decimal. See the two ways you could do it? So yes, your math teacher does want all of you to remember that tangent's equal to 1 at pi over 4. The fact is that a lot of people don't. You could just inverse it on your calculator.
Is it also equal to 1 at...
What's that?
How do we know it's the tangent inverse of 1?
So you're trying to figure out where is tangent equal to 1. So I inverse that. And so now the tangent is gone. I'm left with 2x is equal to
Oh, yeah.
pi over 4.
Okay.
So, yes.
Is tangent equal to 1 at 5?
5 pi over 4 as well. Yep.
Oh, that also.
Yes, but we'll just find the first one. Yep. And then to solve, I divide both sides by 2. And I get x is equal to pi over 8.
Because pi over 4 divided by 2.
Okay. Are we okay with tangent of 2x equal to 1?
Yeah.
Okay. So if I could just bring your brains back for a second to understand this piece. So what we want to do is we want to get at x, right? Like that's the whole idea. So how do we get at x? And I'll show you how you got to remove tangent. Can you divide by tangent? No. What you have to do, and you don't have to write this out, but this is the operation. We tangent inverse both sides. I just assumed that we remembered that from our review and from last year, but we did not. That's okay. So what happens on the left side? The tangents go away and you're left with 2x equals whatever tangent inverse of 1 is, and or 0.785. So I'm going to write pi over 4. Now, what happened is the tangents went away, the 2x still remains. So at this point, sometimes people get caught up with the dividing by 2. How about instead we multiply by half? Are you okay with getting rid of the 2 that way? And the x is pi over 8. So if I look at my function really quick, sine of 2x plus cosine. What? Plus cosine of 2x. And if I zoom standard, hopefully I'll see that this function, which looks similar to a sine or cosine function, it looks like at pi over 8, does it have a local max? Yeah, and in fact, Ella said, Mr. Gentz, if pi over 4 works, then would also 5 pi over 4 work? She is correct. That would be then where it has a local min. In fact, the number of local maxes and local mins is an infinite number, isn't it? I would just be asking you to find the very first one. Okay, the very first one. So, you guys are set to go to work and ask some questions. I'll come around and help you. There is some algebra within your worksheets. Some people need the worksheet from yesterday, right? Yeah. Would you like the rest of your homework now, or do you want me to give it to you tomorrow? Okay, so I have all that printed off, ready to go for us to assemble. Who else needs the worksheet from yesterday? For the last test, yeah. Yes. Yes.